Hey everyone, let me turn on my light. I'm Will. Welcome to miniKanren uncourse Hangout number 4. We talk about miniKanren, relational programming, pure logic programming, all those sorts of things. And today we're going to talk about a really cool topic, which is relational interpreters. And we're going to write an interpreter for a subset of the scheme programming language in miniKanren and see what sort of tricks we can play with it when it's written in a purely relational style. In order to do that, we need to know something about writing interpreters. So the first thing we're going to do is try writing a little scheme interpreter in Scheme, just so we understand how the parts work, and then we'll translate it to miniKanren. Okay, so that's the plan. There's a lot to say about this topic, a lot to say about it. In fact, I'm trying to work on some blog posts and things like that. Part of the problem is that one of my proto blog posts has 3,000 lines just talking about 1 or 2 ways to represent environments, and I think I know at least a dozen ways to represent environments in a relational interpreter. So you can go very, very, very deep with this, and I've been working on this for a couple years now, and I feel like I'm only scratching the surface. But anyway, I can hopefully show you why I think this stuff is really fun and cool, and can talk about maybe a couple of the open problems. But I mean, honestly, could do many hangouts just on this relational interpreter stuff because it's so fascinating. And there are other types of relational interpreters that we could look at also. But this is kind of the one that really grabbed my attention. Was one of the most fun programs I've ever seen or worked on. It's really neat stuff. So we're going to do that today. Okay, so the first thing we're going to do, like I said, is we're going to do a little or create a little interpreter in Scheme for a subset of Scheme. And then we'll go to miniKanren. And we're going to try to live code everything from scratch. We'll have an implementation of miniKanren, but otherwise everything we're going to do is we're going to try to do from scratch. So hopefully it'll work. If not, I've got backups of things, of places we can grab. But I think we'll be able to pull it off. But there's a lot to do, so let's get started. As usual, any questions, feel to put it, free to put in group chat or in the IRC channel. And I'll try to check those periodically, okay? If anyone sees anything, any questions in the IRC channel that they think are really relevant, if you can put them in group chat, it's easier for me to see those sometimes. All right, let's begin. Time to begin the screen sharing. Get our Emacs on. Okay, I'll do it a little wider. And let me bump up the font size a little bit. Try to get below the logo. Okay. All right, the first thing we're going to do is create a little scheme interpreter for a subset of Scheme that's called the call by value Lambda calculus, whatever that is. Basically, it's what Scheme is based on. And so let's just look at that for a minute. All these topics I'm going to talk about, you could spend a career studying, at least a career, maybe many careers studying any of these topics. So I'm not going to get into the details of all these, but we can talk about a few of the things going on. So in Scheme, there are 3 types of Scheme expressions that are really important. They're really fundamental. And that you really need those in order to have a Scheme or a Lisp. And those 3 things are variables, so like the variable x. And if I hit return, I can see that when I try looking up x, I get an error because x isn't bound. I can define x in Scheme in various ways and then look it up, and then I'll find the value for it. So one way to do that in Scheme is something called define. I can define x to be 5, and now if I look up x, I get back the value associated with x, 5. Okay. So we have variables like x. Another thing we have is something called lambda. And in other languages, you might hear of these as anonymous functions, functions that don't necessarily have a name associated with them. Anonymous procedures, whatever you want to call them. And in this case, I could create a function, lambda yy, let's say. And I'm typing lambda, by the way, as Lambda, and this my Emacs turns it into the Greek lambda symbol. So lambda yy, this is creating a new anonymous function or procedure that takes one argument. In scheme syntax, this list of arguments takes length 1. I could make it take 2 arguments, y, z, if I wanted to. In this case, I'll take one argument, y, and then the function is going to return whichever expression is in the body of the lambda. In this case, it's just y. So this is the identity function. This is a function that takes some value and returns that value. And if I hit return, you can see that I get back this hash procedure thing. Okay, so something representing a procedure in Scheme, we'll actually see one way to represent procedures today, at least, when we write our interpreter for this language. The interesting thing about Scheme procedures is that you can treat them as first-class values. So, for example, you can actually create a list containing Scheme procedures. Now we get this parens around it, so we have a list containing them. We can take the first thing in the list to get the procedure back. You can see there are no parens on the outside. So we can do anything with a list that we can do with other values, or sorry, with anything with a procedure we can do with other values, like stick it in a data structure, or pull it out of the data structure, and so forth. The main thing we can do with the procedure, though, the most important thing we can do is we can apply the procedure to some arguments. So when we have lambda yy, which represents the identity procedure, what we might want to do is apply that to 5, let's say. Okay. And the way we apply a procedure to some argument in Scheme is wrap parens around it. That represents a procedure application or a procedure call. If I try evaluating that expression, the application, I get back 5. So I'm applying the identity function to 5. I could also put in a sub-expression that isn't a constant value like 5, but which will evaluate to 5. So plus 2, 3 in Scheme will evaluate to 5. And the way this expression works is that Scheme in some unspecified order, let's say it goes right to left, we'll first of all see that we have a procedure application with these parens. Secondly, it'll see that there are 2 subparts to this application. There's the lambda expression and this call to plus. So say the application goes right to left, the plus 2, 3 will be evaluated recursively. So whatever the rules are for plus and so forth. This will give us 5. And then the lambda yy will be evaluated, and that will give us a procedure, some representation of procedure. And then the procedure will be applied to the value 5. And then we get back 5. Okay, so there are a few steps involved. We're going to go through those when we write the interpreter. You'll see exactly how that works. The reason that we say we have call by value semantics or call by value version of lambda calculus is that we actually have to evaluate all of the arguments before we can actually call the procedure. So plus 2, 3 has to be evaluated. We actually have to get back a 5 before we can call the procedure, the identity procedure in this case. In call by name or call by need semantics, and Haskell is the most famous example of a programming language that uses call by need semantics. Those lazy languages will avoid evaluating the plus 2, 3 expression unless the variable associated with that that argument is actually used. So here we're actually using y in this lambda expression, but if we had something like lambda y6, we know that procedure constructed by lambda y6 always returns 6, and y is ignored. So in that case, we wouldn't necessarily have to evaluate the +2, 3 to get 5, right? Like we don't need to know anything about y in order to evaluate it. But in scheme, the way scheme semantics work, call by value, we actually will evaluate +2, 3 before this procedure gets called. One reason that can matter is maybe we do something illegal, like we divide 2 by 0, and we get a division by 0 error. Okay, if we were in a call by name or a call by need setting, these lazy settings, if we don't actually refer to y in the body of this procedure, then we wouldn't get this error because we actually wouldn't perform the division. Okay, so in scheme we always perform the division. In the traditional call by Lambda calculus, in the mathematical or logical formalism of Lambda calculus invented by Alonzo Church in the 1930s, the traditional version of Lambda calculus is lazy. It's not call by value. So you wouldn't evaluate the argument here before doing the procedure call. Okay, so that's one difference scheme. Turns out most modern programming languages really do have call by value semantics. You do evaluate all the arguments before calling a procedure or a method or whatever. So other than Haskell, most languages that you're likely to have used probably have call by value semantics. Okay. So that's the other. So we've seen basically all the Lambda calculus stuff, right? So we've seen variables like x, and we've seen lambdas create the DA, can create a procedure, like we could have y plus yy. And then we have procedure application, which in scheme or Lambda calculus are just parens wrapped around. So we could, use our variable reference x. X evaluates to 5. That means that basically y is going to be bound to 5. And when we evaluate plus yy, this is going to be the same as valuing plus 5, 5, and we'll get back 10. Now, in the true Lambda calculus setting, in addition to not being called by value, in addition to being called by name, another change is that we don't have things like plus. Okay, and we probably don't even want to worry about variables like x that are not bound, that are bound only at some top level thing, like in the read eval print loop. So we're going to simplify things even more and say we don't have things like plus. We only have application. We only have lambda, and we only have variables introduced by lambdas. So we can have some expressions like lambda x, lambda y. We can start nesting things. We have x applied to y. Okay, so that's about lambda expression, and we can apply this whole lambda expression to another one like lambda z, which is the identity function, and we apply it, we get back another procedure, and so forth. Basically, when we're in this world, everything we get back as value is going to be a procedure. And we can extend this because we probably do want conveniences like numbers and addition and so forth. But one of the important results that Alonzo Church had was he showed that the Lambda calculus is powerful enough to express any form of computation that we might be interested in, any of the computable functions that we want to compute, and it's equivalent in power to a Turing machine. In fact, Alonzo Church came up with this notion before Alan Turing came up with the Turing machine notation. Okay, so this is equivalent to a Turing machine. It looks very different and kind of feels very different when you're programming with it, but you can encode the Turing machine just with the lambdas and the application and the variables. You can encode arithmetic, you can do anything. And it's very interesting to see how you can encode all those things. I'm not going to get into that right now. Matt Might, for example, has some really cool blog posts about encoding different things like addition, arithmetic, and lambda calculus. I can include some pointers to that. But we're not going to get into that part. But you should know at least that modern functional programming languages at their core have some notion of the lambda calculus. You have application, you have some way to create procedures, you have some variable reference. And they might be called by value semantics, they might be call by name semantics, probably not. Might be call by need semantics, which is sort of like call by name plus some memoization. But all these languages that you see that are functional or Lispy or whatever, they have at their core the Lambda calculus. So that's the thing we're going to implement first as part of our interpreter. Okay. So let's go ahead and define an interpreter. And let's call this eval. I'll call it eval exp, eval expression. Yeah, whatever we want to call it doesn't really matter. So we're going to call it eval expression. And this is all defined just in scheme, not in miniKanren at this point. What we're going to be defining is what's called an environment passing interpreter. So we are going to take an expression, like expr, and we're going to take an environment env. So one thing we want to do is be able to tell what sort of expression we have. And we're going to do that by using something called pmatch, which is not built in the scheme. It's defined as a macro. Oleg Kiselyov came up with this thing, pmatch. And if you're interested in how macros work in scheme, or the power of macros, this is actually not a terrible place to start. It's a neat pattern matching macro that's based on success and failure continuations to do the pattern matching, and it's similar in many ways to the matcher built into Racket, for example. Okay, the pattern matching turns out to be very convenient sort of abstraction, so lots of languages have those built in or as extensions. So what pmatch is going to do is when we match on an expression, we're going to be able to write down an expression that looks very similar to what we want to match against. So if we want to match against the lambda expression, say we have a lambda expression that takes a single argument, then we could write that as something like this. Okay, so this is the pattern. And then we have sort of the body of the match, like whatever we want to return here. So if I wanted to return 5 for some reason, that's what would be returned for this match clause. Okay, and the body of the match clause is only going to be be evaluated if the pattern matches against whatever we're matching against, which is in this case is the expression. So if we want to go ahead and get our lambda calculus set up, we can go ahead and get our patterns going. So this would be an application. You have some expression applied to another. Here we have a lambda, also known as an abstraction. And then the third case for lambda calculus is when we have something that's just a variable, like that. I'm using commas here to represent variables. Implicitly, in pmatch, there's a back quote in front of each of these patterns. It's just suppressed because every pattern has it. If you use something similar in Racket, you have to put the back quote there if you want the back quote. So we're creating a back quoted or quasi-quoted list. So in this case, for example, we can see that we're creating a list, and the lambda part is just going to be the symbol lambda, and these parens are constant data also. But x could match against anything. Body could match against anything. If we really wanted to be conscientious about this, we could add some additional guards to this form saying that x has to be a symbol and so forth, and body has to be a lambda calculus expression. So we can kind of bulletproof our matching. Right now, I'm just going to assume that all of our programs are correct syntactically. We could always add, so another piece of code to ensure our programs are correct syntactically. I'm just not going to worry about that right now. Anyway, because everything is implicitly backquoted, we have to put a comma in front of the x for this to work. So that means that x is something representing a variable. In order to really match against just variables, not against anything, because it turns out comma x matches against any pattern you might possibly imagine, we need some additional guarding, if you want, we're going to say that X has to be a symbol. So like a quoted symbol, like foo, quote foo. The expression quote foo will return the symbol foo, and we're going to treat things like quote foo as variable names, or as variables. Okay. So if that's the case, then we're going to return something. The other cases we'll return something else, maybe. So that's it. That's our little interpreter. And we have this guard thing here, making sure that we're only going to match against the variable case when we have a variable. In fact, if I want to make sure that I've got the right cases here, I can say abstraction or lambda and application. We can already test our interpreter and make sure that we're pattern matching against the right types of expressions. Okay, and whenever we're doing things like building interpreters, especially if you haven't had a lot of experience building interpreters, it's good to try to test things as quickly as possible with as small changes or small improvements as possible, just to make sure that any errors you catch, you're going to catch quickly, because otherwise it's very difficult to debug these things. So let's go ahead and try testing our tiny little interpreter. Hopefully we got it right so far. Okay, so let's try calling eval_exp on quote foo, which I said I hope to be a variable. Ooh, did I not? Oh, sorry, loaded the wrong file. Let's load transcript. See if that works. Incorrect number of arguments. Ah, I forgot to include the environment. So let's say we have some empty environment, which we're going to represent as the empty list. We'll get to that in a bit. Okay, so foo, quote foo, or quote x, those are variables. We could try writing something like lambda xx. This is a common gotcha of writing these sorts of interpreters in Scheme. If we try evaluating this, we'll get an error saying the match failed. The reason the match failed is that we forgot to put a quote in front of the expression. Forgot to quote the expression, and what that means is that Scheme will actually evaluate the lambda xx, which will just create a procedure in Scheme, and we'll be trying to match against the procedure. So we need to match against just the expression, the quoted expression. So we need to put that quote, not a back quote, just regular quote works. Sure enough, we get an abstraction. So if we put an x, that's a variable. We put lambda xx, something like that, that's an abstraction. And if we do an application, something like that, sure enough, that's an application. Okay. And the way match works, or pmatch works, is it's going to try matching in order. So if any of these clauses match, then that's the answer you're going to get back. It's like the way cond works. As opposed to a condy that tries every clause, here we just try the first one. If that matches, we're done. Okay. That's why it's important to guard this comma x pattern, because otherwise everything will match against that. In fact, I can demonstrate that. So if I load my eval_exp again, if I try this, now it says, uh-oh, everything is a variable. Okay, so that's no good. We need to make sure to have this guard for the comma x pattern. Whoops. The other thing we have to be a little careful of is the ordering of the clauses. Okay. So the lambda is basically safe because lambda itself acts like a tag that tells you what sort of expression it is. So lambda is generally safe, and furthermore, this list is length 3, so that's not going to overlap with application, because in this case we're going to assume that every lambda expression has one variable. It's called curried representation of our lambda expressions, and application. Every procedure application, we have one argument being passed in. Okay, So by doing this, we make sure our application and our lambdas don't overlap. But if we were to allow any number of arguments in an application, we have to be careful, because then the list of the application could be link 3, which would match our abstraction clause. So, the application line might think that this lambda tag, this symbol lambda, actually refers to a variable called lambda. And if we believe in lexical scope and shadowing, that's perfectly fine. I mean, we can write this in Scheme. We can have a variable named lambda. That's a perfectly reasonable thing to do in Scheme. So now this lambda isn't the lambda that creates a procedure. It's just this variable. And that's the same as lambda. We could have called this lambda xx and applied to 5. We can just as easily call it lambda, lambda, lambda. I don't know why the last lambda doesn't isn't typeset nicely, but those are exactly equivalent. Okay, so if you believe in things like lexical scope, then you really can have an application that has lambda in the first position. I'll show you an example of that, actually. We can have lambda of 5, and I'll pass in the identity function, lambda xx, as function being passed in. Okay, so I have the identity function being passed in, and this lambda, and then this lambda up here, this lambda variable is going to be bound to the identity procedure, identity function. So this lambda 5 is actually applying the identity procedure to 5, and sure enough, it works. And in fact, you can play these sorts of games all day. If you can build up examples where things like lambda x5, the x is actually just referring to a regular variable, and this lambda isn't lambda that constructs procedures. It just happens to be some other thing. So you have to be very careful to make sure that that you don't run into trouble, and you actually can handle those things properly. Let me see if I can construct an example real quick of this. So let's do, I'm going to make my lambda y also be an identity procedure. Or sorry, yeah, I want that. I want lambda y, sorry, to be a procedure of no arguments, say, that returns 6. Let's see, did I get that right? Lambda y. Y with no arguments, 6. Oh, okay, because this lambda now has to take 2 arguments, so that has to be like that. Yeah, okay, so I was able to build something that looks like a regular lambda expression, but has very different semantics. So this lambda is actually bound to this procedure, which takes 2 arguments and returns its first argument. That y, this list containing y, this isn't introducing a new variable. Rather, this is actually a procedure call to a thunk, a procedure of no arguments that just returns 6, but we're ignoring that value. We could return, actually, yeah, so in this case, it's the value of x is being returned is the value of 6. So it's this call to a thunk that's returning 6. Okay, so that, I have to think through that for a second, but that all makes sense. So we're allowed to redefine lambda and do anything we want. So we have to be careful when we do pattern matching that our pattern matching handles this. And if we were to allow multiple arguments for our application, we'd have to be careful and make sure that we could distinguish a true application from an abstraction. And we can do that by looking up variables in the environment and stuff like that. So there are a couple of different ways to handle that. Anyway, I'm just trying to point out that there's a lot of subtlety in getting this right once you start extending this to handle multiple arguments. There's subtlety in getting it right in terms of the guarding of this variable and so forth. So even now we have some subtlety we could be caught up in. Once we get to miniKanren, it's going to be trickier because In miniKanren, remember, we're going to have something like a cond doing this work, and the cond is going to try every single clause. So we can't rely on the fact that the first match is going to take effect. We have to make sure that our different clauses don't overlap at all, including the variable clause. So it starts getting tricky. Okay, we're going to need a little bit more help. All right, so let's go ahead and try to handle variables. In order to handle variables, we're going to need some environments. All right, so in the variable case up here, what we want to do is figure out what value, if anything, is x associated with. And we can do this by basically looking up x in the environment. That's all we do. We just need some helper to look up x, and we need to decide how we're going to represent environments. There are lots of ways we could represent environments. We can do sets, we can do all sorts of things. But we're going to use association lists. Okay, so an environment is going to be some sort of mapping from a symbol representing a variable to some value. Okay, that's what an environment is, and it's going to look like an association list. So, for example, we could do something like x.5 y.t. That would be a legal environment where x and y are variables, and x is bound to 5 and y is bound to t, that's true value hash t. And if we looked up z in this environment, we would get an error because z isn't bound. Okay, so that's an example of what an environment might look like. Now we're going to define something called lookup. And a call to lookup, we want lookup to be something like, if we look up y in this environment, we want that to return hash t, the value associated with. Actually, I'll say it's a list containing hash t and foo or something. We want whatever value y is associated with in the environment to be returned. So that's the behavior we want. Let's go ahead and define lookup. It's very simple to write. We can write this in several different ways, but we have some sort of variable, we can call it x, and some sort of environment, which is an association list. I'll do it in, you can use a bunch of scheme helpers in various ways to make it really short. I'm not going to worry about that. I'm going to write as a little recursive procedure. Because it's recursive, we're going to have to make a choice. I'm using cond. I have two tests, basically. Just a reminder, these square brackets are the same as the rounds. They're just, I use them to visually distinguish what I'm doing. All right, so one test we have to make when we're recurring on the environment, which could be of any length, we have to know, is the environment empty? Is it null? If so, we have an error case. So say maybe error and lookup, unbound variable, let's say. Okay, whoops, error. Okay. Else, if the environment isn't null, we want to check to see if the first thing, the first pair in the environment, so the environment's going to have pairs of variables to values. So what we want to know is if that variable is the variable we're looking for. One way to do this is to see if the car of the environment is equal to x, and if so, then we're going to return the cooter of the car and all this stuff. Well, that starts getting confusing with all the cars of the cars and all that stuff. So let's define lookup a second way using our pmatch friend. And this should make things more clear and also hopefully make it more clear what pmatch is doing. So we're going to p-match on the environment. I have a couple of clauses. One clause is when the environment is empty. Remember, that's the same as having a back quote of the empty list. So if we match on the environment as the empty list, that's the same as this null test. So in that case, the variable isn't bound, so we can call error. In another case, it's not empty, so we know that structurally the environment looks something like this. It has some variable called y bound to some value, v, and there's the rest of the environment. I'll call that env rest, or env hat maybe. Okay. All right, so structurally that's what the environment looks like. And remember, there's a back quote there implicitly. So we have some pair representing a binding, and then the rest of the environment. So in this case, what I want to know is whether now that variable y is what I'm looking for. I could say if x is equal to y, then I've matched. In that case, return the value that they're associated with. If x and y are different, then I need to recur. So I could look up, still going to look up x, that's the variable I'm looking up, but I want to look that up in the rest of the environment. Like that. Okay, so this is the pattern matching version of lookup. I'll get rid of the one with the cars and the cutters and all that, because that's really annoying. Another way we could define lookup that would be very similar in spirit, we could pattern match two different ways. Well, I'm not even going to get into that. I think this works actually. Let me make sure I have the right version of pmatch. Pmatch semantics are right. I think this will work. In this case, we can just kind of ignore this value. So I'm going to try to do like sort of the true pattern matching version with a guard. In this case, we want to say, oh, okay, yeah. Never mind. Here's how we can do this. Yeah. Guard EQ of x and y. In that case, return v. Otherwise, we're going to recur. All right, so this is a more pattern matchy version of the same code. In this case, we're going to say, well, when we have an association list and y is associated with v, if we have this extra side condition saying that x and y are the same variable, then just return v. Otherwise, because we didn't match on that, we know that y is not the same as x, and therefore this value could be ignored. I mean, if we wanted to, we could call this underscore or something. And depending on your version of match, you might actually just be able to write a regular underscore. So in other words, we don't care about this value because we're going to have to recur. So in that case, we're going to just look up x and env. And depending on the pattern matcher you use, you may or may not be able to just put an x there and get rid of the guard. So that depends on the pattern matcher you use. But metaphorically, this is one way to write lookup. Okay, so both of these should work, and it's a matter of style, which one you prefer. Okay. I think. Let's try going for the second one. All right. So let's make sure that this lookup works. Hopefully it does. Let's try our little test. Okay. And if I look up z, unbound variable. Okay. And if I look up x, I should get 5 back. Okay. So it looks like we're doing all right with our lookup. We have a pattern matching version of variable lookup. We're looking up some variable in some environment. And that's all the variable case in our interpreter is going to do. Okay, so that's one of the 3 clauses. And let's see. Okay, Daniel asks, if you shadow the symbol lambda in some lexical scope, you can no longer create new abstractions within that lexical scope. That's true unless you have some other mechanism like modules where you can import the old lambda, or you could define your own macro that uses, I mean, there are ways to get around it, but that's true. And in ShadeScheme, for example, there's a module mechanism that will allow you inside any form to get your hands on the original lambda. So that turns out to be really useful if you want to do things like redefine lambda, because in Scheme, redefining lambda turns out actually to be really helpful. I often redefine the lambda syntax to do different things. Okay, so we're 1/3 done. And remember, this lambda calculus interpreter, even though it's very short and simple, this is Turing complete. I mean, we're going to be interpreting a language that can express any computation you can imagine, as long as it doesn't have things like input and output and stuff like that, right? But from a pure computation standpoint, this is extremely powerful. And I'm not going to talk about quantum computing and that kind of thing. Okay, abstraction. How about abstraction? Okay, and then application. We have abstraction and application next. Those are the two remaining things. So for the abstraction case, what we're going to do is create some representation of a procedure. We have to have some way to represent a procedure. There are different ways to do this. One way to represent a procedure is using a scheme procedure. In fact, you could use a scheme procedure to represent an environment as well. You can do all this stuff in what's called a higher order style. I'm not going to show that. It's really neat. But for going to miniKanren, we actually want to use data structures that we can match on. So I'm not going to show you that approach. If you really want to know about that, then I can talk about that another time. Dan Friedman, in his course at Indiana, shows that as the first approach to writing interpreters. He always shows the higher order version. And it's a very neat thing to see. And it's very, very short. You don't need any helpers if you do it right. It's really, really cool, really clever. I'm not going to show you that right now, just in the interest of time. If people want to, I can show it to you later. So we're not going to use a scheme procedure to represent a procedure in our language. We're going to create a data structure, okay? And we could use it. We could create a data structure using list or cons or whatever. We're going to follow our pattern matching approach and use the back-quoted list. But we could construct the same list with cons and quote. We're just trying to make the list look like data. And something we can pattern match against, actually, as we'll see in a minute. So I'm going to create a list that's a tagged list. We're going to have a tag at the beginning of the list, just a symbol at the beginning of the list, tongue, specifying what sort of data this is. And that allows us to distinguish between the different types of data we're creating. I'm going to use a closure tag. So the symbol closure represents that this is information representing a procedure. I could also call it proc, if I want a proc tag, procedure, or whatever. I can call it anything I want. Closure is the sort of traditional technical term for what it is we're creating. Closure representation. Okay. And the closure is going to have a couple pieces of information. And you can build this a couple different ways. I'm not going to get into all the details of how you can do it. Once again, Matt Might has a nice blog on this if you want to learn more about different ways to represent closures. He does it in a slightly different way than I do it, but I'll show you sort of the Indiana way. There are three pieces of information you have to store in a closure, metaphorically, for it to work, to give you lexical scope, to give you all the shadowing behavior and all that. The three pieces of information you need are the variable coming in. You need the body that you're going to be evaluating, this body, so x and body. What Matt does is he just stores the entire expression as a single argument in the closure. So that's how what he does is a little bit different. It still has the same information, so it doesn't matter. Still the same three pieces of information. So you have the variable, you have the body, and then you need this environment thing, because we might need to look up the value of a variable when we evaluate the body. So we need to store the environment. Storing the environment is the critical piece. That's what gives us the lexical scope. And if we store, if we don't store the environment, then there's no way to get the behavior of scheme with the shadowing of variables and all that in the nice way. Okay, so we need to store the environment. Or if there is some way to get lexical scope back, we're going to have to do something different, substitution-based approach or something like that. There are other techniques you could use, but the way we're using it, we need to store that environment. All right, so that's what a closure is. And we can, at this point, once again, we can test our code. So fine. All right, load. I think something changed with my Emacs recently. Okay. Sorry, so let's do our eval exp. Okay, so variable, unbound, good. How about a variable in a bound environment, y bound to 5? That works. Let's try a lambda. Let's do a lambda zz in, say, the empty environment. That gives us back a closure. Z, the body is the empty environment. Let's make the body a little more interesting. Z applied to Z. Okay, so our closure has 3 parts. It has the formal parameter, the identifier Z, has the body, Z applied to Z, and it has the environment that was in place when the closure was created. If we start out with a non-empty environment, say y is bound to 5, we'll see the closure closes over that environment. Okay, we remember we were created in the environment where y was bound to 5. Okay, so that's where the closure captures the environment. Great. 2/3 of our Lambda calculus interpreter done. Got variables, abstraction, or Lambda. Now we have to do application. We're using data structures to represent closures. And the way this works is application is going to be where all the interesting work is done. One thing that's interesting is that if you used a higher order representation of procedures, if we actually had this Lambda expression return a scheme procedure representing a Lambda expression, what would happen is that application would be trivial. It would just apply that procedure, and all of the interesting work would go into constructing a procedure here that did the right amount of work, did the right thing. So the Lambda line would get complicated, the application line would be super simple. If you use a data structural representation, it swaps it. The application line gets complicated, the abstraction line is trivial. The Lambda line is trivial. So depending on how you represent your closures, whether or not you use a data structure, a traditional data structure like a list, or whether or not you use a procedure, depending on representation, the complexity will be in different parts of your interpreter. So anyway, we're going to use the data structural version. And in order to evaluate this application, what we really need to do is evaluate E1 and evaluate E2. Those 2 sub-expressions. Hopefully E1 will be a proc, or a closure. Better evaluate to a closure. Okay. And say the closure, we'll call the closure that we get, proc, I guess. E2 is going to evaluate to some value val. And now we're going to, the last thing we'll do is we'll apply the procedure to the val. Okay. So those are the 3 things that have to happen with the procedure application. Now, one thing that's important in scheme semantics is that we have to evaluate both E1 and E2. Evaluating E2 is what gives us our call by value behavior. But the order in which we evaluate E1 and E2 is unimportant, and it's unspecified in scheme. We could evaluate E2 first. It's up to us. Different implementations will do this differently and in different contexts. And sometimes Shea scheme will evaluate E2 instead of E1 when it thinks it's going to be faster or whatever, or if it makes the implementation simpler. You're not allowed to rely on the order of evaluation of the arguments in an application in scheme. And I've made this mistake before. I did stupid things like put side effects inside of the expressions, like random number generators and things like that. And it turns out that different implementations of scheme will evaluate them in different ways. So we can't assume the order. We have to pick an order. Okay, but any order we pick is right. So we could evaluate E2 first if we wanted to. It doesn't matter. We go right to left, left to right, flip a coin, whatever. Okay, let's go left to right, E1 first. Doesn't matter. It matters a little bit when we get to miniKanren because there's orderings that will allow us to prune the search better. But like I said, E1 had better evaluate to a proc or a closure. Let's call it a closure. And if E1 doesn't evaluate to a closure, we know that something's wrong. Okay, we can cut off that branch of the search. So that's why in miniKanren we might want to evaluate the E1 first. It gives us a chance to fail when the information doesn't line up. Of course, we also have a chance with E2 because if we know E2 is supposed to have some particular value and it doesn't produce that value, we know that's inconsistent also. Okay, so let's go ahead and evaluate E1. How do we evaluate E1? Well, if only we had a procedure that could evaluate some expression. First, we're defining that. We believe in the power of recursion, so we'll just call eval exp. If we call eval exp on E1, we have to decide what environment to evaluate it in, but that will give us the value of E1. Similarly, with evaluating E2, we have to decide on what environment we want to evaluate E2, but that will give us hopefully some value. And then we can apply the value we get back for E1 to the value of E2. All right, so which environment to use? Well, we really only have one environment at this point. We only have env. So that's really our only choice. Remember that our closure has an environment, but we don't have the closure yet. We have to evaluate E1, which we know nothing about. E1 could be an arbitrarily complicated expression. E2 could be arbitrarily complicated, right? In fact, these, E1 or E2 or both might also go into infinite loops, right? They really could be anything. So we don't know anything about E1. We don't know anything about E2. We only have our current environment env. We have to evaluate E1 and E2 in env. Okay. We also, one thing we might want to do is start giving names to these things. So we might want to say let proc. Now I guess I'll go back to proc. Names are hard, right? Okay, so we could say proc. Value of proc is going to be the value of E1. Similarly, we could call val the value of E2. Now, if you know about how scheme works, you know that the reason, you know that there's an implication in doing it in a let like this. So the let expressions, the right-hand side of let bindings, these two evals, can't refer to each other, and they happen in some unspecified order because let really turns into lambda. So we don't know if the evaluation of E1 will happen before E2 or vice versa. So by putting both of these in a let, this is actually a hint to the reader. We're giving the reader an important piece of information that there's no dependency between proc and val. Those can be evaluated separately. They could be evaluated in parallel. In fact, there have been attempts to do parallel versions of functional programming where you actually do evaluate the sub-expressions in parallel. Once again, if you have side effects and things like that, you have to be careful. And in scheme semantics, you do have to pick an ordering. So parallel evaluation in scheme only works if there are no effects within these sub-expressions. But you can do it, subject to certain restrictions. Anyway, there's certainly no dependencies between proc and val. So proc might be evaluated first, val might be, these expressions, E1, E2, either one will be evaluated first. And now, once we have a proc and a val, then we can do something with them, okay? Well, what I might want to do is p-match on proc, because proc is going to be a data structure. And in fact, proc is going to be a closure, and it's going to look like this. I can just take the pattern without the back quote and just plop it down in a p-match clause, and this will destruct or tear apart the value of the procedure and give me the parts of the closure. If this if proc doesn't match against this closure, it's not a procedure, and we probably want an error. So maybe I'll put an else case. I'm putting a comma here because different versions of pmatch either do or do not support an else. But if you put a comma before else really just is some pattern that matches anything. So it's a bit of a hack. But I can put an error here in let's call it val proc, I guess. Whoops. I guess this is some new Emacs magic having to do with quotes and stuff. I don't like it. Could be a way to turn off. Okay. Eval exp, we'll say E1 does not evaluate to a procedure, let's say. Okay. Exercise at home is to clean up the error messages and all that. Make it nicer. Oh. Looks like something really did change in Emacs. Okay. Now, we're going to evaluate the closure now. How do you evaluate the closure? Well, to evaluate a closure, we're going to evaluate the body in an extended environment in which the environment of the closure is extended with a binding between x and val. Okay, so what does that mean? It means that we're going to evaluate body, the body of the closure, the body of the Lambda expression that we had up here, this body. We're going to evaluate that body in an environment. Which environment we're going to use? This is the critical part. We're using the environment that was stored in the closure. That is not necessarily the environment that we evaluated proc and val in. This can be completely different environment. So what I'm doing here is this use of pmatch. This env is shadowing these two envs. You could call that env hat if you want to show that it really is a different environment. Okay. Since we're schemers, we tend to just shadow everything. But this env and these two env are not the same env. And we need to make sure, to get our lexical scope right and shadowing and all that stuff, that we evaluate body in this environment that was stored in the closure. That's why we store it in the closure. But we have to extend this environment with an association between the formal parameter x that we got from the Lambda, this x, and the value of the argument passed into the procedure, this E2 thing, okay? Which is the same as this E2 right here. All right, so what does that look like? Well, we are going to do a procedure evaluation, which is, we're going to evaluate body by making a recursive call, evaluate the expression being body in an extended environment, okay? And we can call, we can write a helper called extenv that's going to extend, the current environment with x and val. We can do it that way if we want. I'm going to cheat a little bit and say, okay, we know, I'm going to, we're just going to expose the fact that the environment is an association list. So we'll take env, and we're going to cons on to env a pair. And that pair is a pair between binding x to val. So we could do that with conses. If we want to be all pattern matchy about it, which I like to do, the extension is going to look like this. Okay. So now it really does look like an association list we're building up. We're creating a new extension, a new association between x and val, and adding that to the beginning of the new environment, or to the old environment, sorry, that was saved in the closure. One important thing to realize about this code is that env itself could contain an association between x and some other variable. So we're shadowing x. If there's a binding between x and 5, let's say, and val is 6, now we're adding association between x and 6 at the front of the environment, and when we do an environment lookup, we'll see the new association between x and 6. So there is some shadowing behavior going on. The other thing to notice is that if I were to change this use of inv to inv hat, but I didn't change this inv to inv hat, if I change this inv to inv hat, then the code means the same thing. If I don't have the hat, then this inv is going to refer to these two invs, the environment that came into the eval exp. Okay? So I'm going to be evaluating body in a different extended environment. This will not give me lexical scope. Okay? This will give me dynamic scope. So my shadowing and all that won't work the way I expect in Scheme. So this env here is critical, which env we use for the extension. Okay, so just by changing an env here in this one line of code, I can switch between static or lexical scope and dynamic scope. And lots of Lisps got this wrong for a long time, including Emacs Lisp. They basically had the equivalent of having the hat, which is equivalent to not storing the environment at all. Okay. And Dan Friedman loves to show that basically you're one hat away from having lexical scope when you write one of these interpreters. All right, so that is our complete evaluator. So let's test it. Let's load it. Hopefully, okay. See if our Lambda's stuff still works. Good. See if our variables still work. Good. Good, unbound variable. Okay, let's try doing an application now. Say lambda z, identity function applied to y, and I'm going to hack the environment a little bit, and we got back 5. So if you notice what I did, I played a little game. We don't have numbers in our interpreter, but because I can start off the initial environment with y bound to anything I want, instead of starting out empty, I can stick any value I want to on the right-hand side. We don't support booleans either, but I can put booleans into my environment, and now we get a boolean back. Okay, so you can play games with these environments that allow you to support additional values you wouldn't otherwise have. All right, but if I evaluate this in an empty environment, I get y as an unbound variable. I could create another lambda and pass that in. I could do y, and now we should get back, yes, we get back a closure y in the empty environment representing the identity function, that second y passed in. And of course, we can have nested lambdas, and now we have a closure that has, for its environment, a non-empty environment where z itself is bound to a closure. And if you're not familiar with reading Scheme, this is the same as having a dot and an extra pair of parens. They're just suppressed by the printer, but that really is the same as that. Okay. Okay, so we seem to have a working little lambda calculus interpreter. But we can add other things to this interpreter. If we want to, so this is really the heart of the interpreter. Okay, that's the important thing to recognize, is that any extensions we make to this interpreter, in some sense, aren't critical, because we can express everything just through the lambda calculus. It may be awkward, but we can express anything we want. Anything we add, like numbers or conditionals and all that sort of thing, that is convenience, but it's not necessary. Okay, that's a critical point to understand it. This is the aspect that we care about. And anything we change that's really critical, things like adding set bang or continuations or things like that. Well, set bang, for example, to add setbang or side effects, we can break this environment into two parts. Have an environment and a store. Have the environment map variables not to values, but to addresses, and have the store map addresses to values, that sort of thing. And that will affect how our variable works, that sort of thing. Okay? So many of the changes we'd be interested in making will actually have implications with these 3 lines of Lambda calculus. If we wanted to make our language lazy, we would change how application works. We would not evaluate E2. We would defer evaluating E2 until it was referenced. So that would affect application. It would also affect the lookup. So a lot of the critical changes you can imagine to this interpreter will affect one of these lines. Okay. Anyway, yeah, with continuations, it's a slightly different story. But many of the changes we were interested in, they basically are little changes to these 3 lines, and the little changes, any of the changes to these 3 lines can have huge effects on your semantics. Okay, it's really critical. It's like having that hat on the end here completely changes the scoping rules for the language. So any changes to these 3 rules are really big deals. Okay, and to some extent, you can look at different notions of programming and languages based on how they change this interpreter. All right, so that's the basics of the Lambda calculus. I'm going to stop the screen sharing for a second. Any questions about that before we continue? I can check the chat. Okay. All right. Yeah, some people in chat are recommending a really good Prolog book called Clause and Effect. Yeah, it's a great book on Prolog and logic programming. Definitely worth checking out. Dan really likes that book in particular. All right. Okay. Okay, so one quote is the code on GitHub for reference when you're in other parts of the file on the video. Norman's asked this question about the code on GitHub. I'm not sure I completely interpret the question the right way. I'm going to be putting all this code on GitHub, and hopefully it'll be self-contained enough that if you have any questions. And I'm putting all the code from all the Hangouts on GitHub. Oh, is the Emacs transcript available live? Oh, that'd be really neat, wouldn't it? Wow. I don't know how to do that. How would you do that? I guess you could like just check it in, right? Let me go ahead and check in. I'll check it in right now. How's that? I'll check it into GitHub right this second. And that's a good idea. In the future, maybe there's some technology we could use that would make that easier. You know, maybe something like an Etherpad or something like that. I don't know. The tyranny of Emacs is once you get used to Emacs, like you don't want to go to anything else. Maybe Vim or something. All right. Okay. miniKanren uncourse, and let me go ahead and copy. All right. Make dear 15. Let's see, well, today is 12/7. Cool. All right. Okay. Let me make sure sure I got it all set up, and then we will start off on that transcript. So yeah, so in the future, maybe I can just do that. Maybe I can just check in the transcript periodically for people who want to hang out. I want to see it live. That's a really good idea. Thanks. And the only thing I have to do is change my includes, basically. So that'll be loading the right miniKanren implementation. Make sure this works. Yeah, it does. Okay, I'll check it in. Git add, commit. Git push. Okay, the transcript is up there for anyone who wants to follow along. It's under, it's in the miniKanren uncourse GitHub repo that I have on my GitHub account, and it's in Hangouts by date, today's date, which is December 7th, 2014, and it's transcript 4, and if you just load that from that directory in Icarus scheme or Shay scheme, for example, like it should load everything right. In Racket, you might need to change a couple of things. Okay. Okay. And let me put in for the people following along in chat. Okay, thank you. Vanilla posted that in IRC. All right. So yeah, if you load that, you can follow along. I'll try to check that in periodically. Okay, so now we have a decision to make. We can go directly to miniKanren and implement the Lambda calculus. We can extend the Lambda calculus interpreter with a couple of forms in Scheme, and then go to miniKanren. We could extend the Lambda calculus interpreter in Scheme with enough forms to do something like factorial, to really kind of put it through its paces. I think what I want to do, because I want to focus on the miniKanren aspect, is I think we already have enough of the interpreter to go to miniKanren and translate that, show how it works relationally. Then let's go back to Scheme and add a couple of forms in Scheme. In particular, I want to add quote and list, because they turn out to be interesting for reasons we'll see soon. Okay. So let me go back to screen sharing. All right. So I had to change the loads so it works, but looks like it's working okay. All right, so now we have a Scheme version of things. And now let's go ahead and, okay, so this is in Scheme. This is call by value, Lambda calculus. In Scheme, that's what we have. Call by value, environment passing, if we're going to use all the buzzwords, Lambda calculus interpreter in Scheme. Is call by value because in procedure application, we actually need the value of the argument to the procedure before we call proc. Okay, that's what makes it call by value. The fact that we're evaluating E2 instead of just passing in E2, that's what makes this interpreter call by value semantics. As opposed to regular Lambda calculus, theoretical Lambda calculus, which is call by name, where you end up evaluating E2 each time you would refer to that variable bound, the formal variable x. Every time you see an x, you would have to evaluate E2 in a call by name system. In a call by need system, when you saw the first time you saw x in the body and it needed to evaluate it, you would evaluate E2 and you would store that value. And every time you saw an x, you would just reuse that stored or cached value. Okay, that's called by need. That's how Haskell works, for example. Okay, so you can see already that just changing how environment lookup works and how you handle this E2 expression, that already gives you 3 different semantics for how you handle variables. Call by value, call by need, call by name. Okay, very powerful stuff, making small changes to this interpreter. All right, so that's call by value, environment passing. It's environment passing because we have the environment in passed around as an argument. Okay, in the recursive calls, all the recursive calls take an environment, so forth. So we're passing around the environment. If we wanted in the style to handle things like setbang, so destructively update variables, one way to do it, a pure way to do it, would be to add, in addition to the environment, store, which would map addresses to values, and the environment would map variables to addresses. Okay, so there are lots of things we could do. We could also add a continuation argument, which would give us call CC for free, and all sorts of things like that. Okay, I'm not going to get into that right now. Anyway, we just have a very simple call by value, environment passing, Lambda calculus interpreter and scheme. Now let's do the same thing in miniKanren. Okay. Well, what are we going to need? If we look, we only have two functions, right? We have lookup and evalexp. So let's try them one at a time. Let's begin with lookup. Okay, we're just going to play the game we played before of translating scheme code into miniKanren. And we should get a relational interpreter out on the other side where we can put logic variables anywhere we want. That's the theory. Let's see if this works. So that's lookup. And we are going to define something called lookup-o. Okay? So this is what a called lookup looks like. What will a called lookup-o look like? Well, a called lookup-o is going to have an extra argument. So we'll have 3 arguments instead of 2. And remember, the last argument metaphorically represents the output argument. Okay, so we could have a call to lookup-o like this, where all of the arguments are fully ground, there are no logic variables. Or we could have something where we had a logic variable, x here, representing the output, and x would be bound to hash tfoo in this case. Or we could put logic variables anywhere else we want, and we could do things like put a logic variable here representing the variable we're looking up, right? And hopefully we would get, quote, y in this case. So we should end up with lookup-o being very flexible. All right, so that's what our lookup-o looks like. Metaphorically, it's still mapping a symbol to a value. Okay, it's just that the environment and the symbol representing the variable and the output value, any of those we can replace with variables. We can put variables inside of data structures, anywhere in there. All that sort of thing. Okay, so let's begin. Lookup becomes lookup-o. That's just by convention. We need an output argument. We'll call it out. Okay, so add a new argument representing the output. Pmatch. We can't use pmatch anymore. miniKanren doesn't have pmatch. miniKanren does have something called match-e, which is a pattern matcher. We could use match-e. I'm not going to use that right now. The reason I'm not going to use that is that it, I think, adds a little more mystery to miniKanren, which is already mysterious enough. The other thing is match-e does some things with variable scoping and shadowing that can trip people up. So the way I use match-e is I'll write my program using condy, and if I want to clean it up, make the code really short, I'll replace it with match-e. Current implementations of match-e in Scheme also have some performance implications. They do a little more work than they should. I'm not sure about the matching in Clojure or Core Logic. David Nolan is a very good engineer, so I wouldn't be surprised if the pattern matcher in Clojure is a lot more efficient, because David knows a lot about making efficient pattern matchers. Anyway, I'm not going to do matchy. Okay, we're just going to do a condi in this case. It turns out that with unification, we can write the clauses very similar style, so it's not so painful actually to be giving up the matchy, because we can still show the structure of the lists. All right, so just to refer to what we're writing, just as kind of like a cheat sheet to remind us what this code is supposed to do, I'm going to include commented out code what the original clauses were doing in the scheme version of lookup. Okay, so we can write this using 3 clauses, potentially. The first clause already gets interesting. Okay, so if the environment is empty, which we could represent as unifying env with the empty list, in that case we're going to fail because the variable isn't bound. Well, if we fail, that means there's no answer to be had, like it's inconsistent information. So we actually don't need that clause at all. In miniKanren, we don't bother with it. Hey, if that's going to fail, we just ignore it. So that is gone. Our code has actually become simpler. All right, forget that. No errors for us. Now I should say, because that's a little bit of a cavalier attitude, perhaps. We might actually want to somehow represent the fact that we can have an error state in that case. Okay, maybe we really do want to be able to keep track of errors, or more interestingly, generate programs that are erroneous or would give you an error at runtime. And in that case, you really would want to explicitly model the fact that you have an error state, and maybe even the particular error message, and maybe have the error message as one of the output arguments, something like that. And therefore, be able to actually say, when running backwards, generate scheme programs that give me unbound variable errors, or whatever sort of error state you want to represent. That's actually a fun, interesting game to play, and I haven't really done much with that in Scheme. So that might be interesting to see what sort of programs you can generate that are erroneous. And this is the sort of thing that, to some extent, John Regehr does at Utah. He does a lot with testing programs. He's got this C-Smith tool that will generate random C programs for testing. So in that case, if you want to write something like C-Smith in relational style, you might actually want to be able to parameterize it by the error and start generating programs that give you that error in whatever language you want to model. So even though we're not going to model the error case, I'm not saying that it's not worth doing or not worth playing around with. It just depends on what it is you want to do. In our particular case, we want programs that don't give errors, but there may be lots of reasons you want to model errors also. Okay. Whoops. I was looking at chat and I messed up. Okay, screen sharing. Back to screen sharing. Okay. Okay, so that first clause is gone. We've already handled it just by being in miniKanren. Making a choice, an explicit choice, that we're not going to handle error cases. Okay. Another case is when the environment looks like this. The environment has that shape, that pattern. Now in this case, because equal, when we're unifying things, it's not really pattern matching in the same way, we actually have to put the back quote on. We have to be explicit about that. If we used matchy, we wouldn't have to put the back quote on. Okay. So we have to put the back quote on this pattern, but otherwise you can just pull up the pattern. The other thing we have to do is introduce a fresh, because these variables like y and v and inpat are not, so those 3 variables are new logic variables that haven't been introduced. So env is okay. We don't have to introduce that in the fresh. In fact, we shouldn't, because env is coming from up here. Okay. But y, v, and inpat, we actually need to introduce those fresh logic variables. That's another thing that matchee takes care of. It will introduce the logic variables for you. That's where you have to be a little careful with the scoping, otherwise you'll get into trouble. All right, so we've done this unification. Now we say the environment has to be non-empty, because otherwise this wouldn't match. And we can ask a question like, or assert that x and y have to be the same. If x and y are the same, which is basically modeling this guard, if x and y are the same, then the output value is v. So instead of returning v, we just unify v without. That is our first clause. The model's first clause. Now, if we want to, we can inline things. We can say that y, because we know that y is equal to x, we could actually replace the y with x in this case, and then we don't even need to introduce the y. Okay, so that's one way we could simplify the code a little bit. In that case, the unification is nicer than the pattern matching of pmatch, because we don't need this guard. We can just use the variable x where we want to. So that's a nice way to write things. I think I'll write it that way. All right. And then we have this last clause. The last clause, we have the environment looking like this pattern. So once again, we're going to unify the environment to be that. We need to have a back quote. Once again, we need a fresh, introduce our fresh variables. Here we have y as a fresh variable, underscore is a fresh variable. If you're used to Prolog, we can't just use underscore in the way Prolog does. We can't write that. For us, underscore is just a regular variable name, and that's not as efficient as it should be. There are technical reasons for that. I don't know if there's a way we can easily get around it. With the matchee, with the real pattern matching, we should be able to handle just regular underscore as an ignore variable, but because miniKanren lets you pass variables around to functions and things like that, we have to be very careful with how we use things like underscore, which is a match anything wildcard. So this underscore isn't really an underscore, it's actually a logic variable that we're just calling underscore. If we wanted two of those in a pattern, we'd have to have like underscore and underscore underscore to be different values. Okay, so that might trip you up. You have to be a little careful. We could call it ignore if we wanted to. Same thing. Okay, so some variable whose value we're going to not pay attention to. And in that case, we want to make a recursive call. Okay, we're not actually going to return the value associated with y, hence the ignore. Instead, we're going to recursively call lookup O, lookup x in the environment, sort of the remaining environment. Whatever that returns will be the output. Okay, so that's how we're going to represent things. There are various ways we could rewrite this code. Another way to rewrite the code would be similar to what we looked at before with lookup. We could do it this way. We could say let y and val be the pattern we want to match, and then we could do a cond. After doing this pattern matching, we could say, okay, if we've already seen that the pattern looks like this non-empty environment, then there are only two possibilities. Either x and y are the same, in which case we want to return val as the output, or we're going to ignore the val and then just recur. And in that case, actually in both of these cases, we have to be careful. And we saw this last Hangout. The problem is these two clauses are no longer overlapping. They don't overlap, or so they are overlapping. In fact, I should demonstrate that. So let me show you what happens with lookup-o if you're not careful. So here's a lookup-o query. So let's say x is 5 and y is 6. Just keep it simple. All right. Load it up. Okay. Let's try this run. We're using the second definition of lookup-o now. Okay, sure enough, y is bound to 6, which is what we expect. X is bound to 5, which is what we expect. The trouble comes in when we have multiple bindings for x. Where x is 5, that x is 5 should shadow the x is 7. In the regular lookup, once we find a binding for x, we're not going to look anymore. Okay, we're going to ignore this x is 7. That's how we can shadow things. Here we get the answer that x is 5, but if we do a run star and ask for all the answers, we get 2 answers back. X could be 5 or x could be 7. So basically what we want to do is ignore any extra bindings for x once we find the first one. The way we can do that is by recognizing that in the first case, x and y have to be the same. That means in the other case, x and y have to be different before we recur. Okay. So x and y have to be different with the disequality constraints. If we add the disequality constraints, then we should be okay. Let me try the new version of lookup. Okay. Now we only get 5 back. Okay, so that disequality constraint is critical in order to preserve the semantics we're used to in Scheme. Otherwise, we won't get true shadowing from our use of the association list. Okay, so that's something we have to be a little careful about. Now, a nice thing about programming in miniKanren is when we're careful, we can actually change lookup-o's code, right? We can reorder this code any way we want. Well, okay. With a caveat. First thing I did is I reordered these 2 cond clauses. Okay, so now the disequality one comes first. So by being careful and explicit, I can ensure the same behavior even if I put the recursive call before that clause, before the other clause, because I am being explicit about when x and y are the same and not the same. Now, when I said I could reorder the clauses any way I want, I could put this equal of env at the bottom. And once again, I'll be able to find 5 as my oh, sorry, I want to look up x. I'll go back. I had the wrong query. So the query I want is this one. So in this query, whoops, I think I just telegraphed the answer to that one. If I do a run 1, I still get back x as the answer. If I do a run 2, well, there is no second answer for x. And what's going to happen is the lookup-o is going to go in an infinite loop looking for that second answer. The reason is the lookup-o call, the recursive call, comes before I unify end with anything. So the lookup-o call, when it's recurring, env is fresh, and env hat basically is fresh because of that. So even if you give a finite, fully ground environment, in the recursive call, the env hat is going to be fresh, and it's just going to keep recurring down longer and longer environments. So the import of this is that if you actually ask only for answers which correctly exist, x is bound to 5, that's fine. But if you ask for a second answer which does not exist, it will go in infinite loop in this case. Okay, so our use of conjunction has nothing to do with swapping these 2 cond clauses, by the way. That's got nothing to do with it. What it has to do with is swapping the 2 goals in the fresh, which is like a conjunction or an and. So let me just show that very explicitly. So here I swap back the cond clauses. I mean, let's go back to the original program. So this is the original definition. Okay, so if I do a run 1, the run 1 always works. A run 2, there is no second answer. Run 2 doesn't diverge. That's great. Fails finitely. Okay. And if I change the 2 cond clauses, the ordering of the 2 cond clauses, run 2 still terminates. That's fine. It has nothing to do with the cond. Ordering of the cond clauses. Okay. So let me go back to the original ordering. Run 2 still finishes. What's important is that unification with env which is going to make sure that inv hat, that argument inv hat, has as much structure as possible. And in this case, we're feeding in a fully ground inv. So inv hat is going to be the remaining environment after looking at the first thing. That inv hat is going to be this list where you have association between y and 6 and x and 7. Okay? Because inv hat is fully ground, we can cut off the recursion. Eventually, inv hat is going to be empty, and then we'll fail. But if I make this unification come after the conD that contains the recursion, at this point, inv hat will not have any structure at all. It will be a fresh variable that we introduced in this fresh. So that means that lookup O, when you ask it for a language, for an answer, it is looking up x in some environment that's basically a fresh logic variable, can represent an unboundedly long, arbitrarily long environment. It's going to keep looking down that list and instantiating as it goes, cuttering down this infinite list, or unbounded list. It'll never stop looking. So that's why run 1, when there is an answer, it will find it. Run 2 is going to go off forever looking for an answer that doesn't exist. Okay? So this is a very important lesson about ordering the goals in miniKanren. In a disjunction or a conD, you can swap conD clauses with abandon. That might have performance implications, but it won't have implications as far as divergence. But in a fresh, or the body of a run, or within an individual conD clause, okay, within a single conD clause, because this is really an and within the clause, you can't just swap these two things arbitrarily. That can change the divergence behavior, not just performance. Okay, so that's sort of a deep insight into how miniKanren works. And by the way, this is a problem that many people have tried to tackle. If you use a true breadth-first search, this problem goes away. You will terminate in both cases. The problem is a true breadth-first search. If you're looking for a deep answer, it'll take you, way too long, and you'll run out of memory too quick. And even problems that miniKanren can come back with in 0 milliseconds or 1 millisecond, will take half an hour or an hour to run, stuff like that, and you'll just run out of memory. So there's a trade-off depending on the search strategy you use. miniKanren search strategy is a biased complete search where basically the conD clauses that come first get more time in the search, and the conjuncts that come first, there's some sort of notion of how much time conjuncts that come earlier get versus conjuncts that come later, and it's not fair. It's not intended to be fair, and it allows you to order your conjuncts in certain ways to make the code efficient, but at the cost of potentially diverging when there is no answer. So that is a very open problem for miniKanren, trying to come up with better search strategies that balance these trade-offs in an easier way, or in a nicer way, or at least gives people the trade-off. It allows programmers to make the trade-offs themselves based on the code they want to write. Okay. If people want to know more about that, I can bring on Michael Ballantyne, who I've been working with on another search strategy, for example. Jim Dewey has a really cool blog post on this. There are a bunch of people who have been trying to tackle this problem for a long time. I can put some links to blog posts related to this up as a resource. Okay, anyway, so that's lookup-O. Lookup-O already is interesting, just from the miniKanren standpoint, in terms of the decisions we made, and also in terms of divergence behavior and all that. So I'll go with the second definition of lookup-O. Okay, here we go. The other thing I can say, let me make sure this, whoops, make sure I get the search order right. Yeah, I forgot to change it back. There we go. The other thing I should say about lookup-O, that's sort of a deep observation. Okay, now it terminates. Is that lookup-O is assuming that we're using a association list representation of environments. Okay, there are many other ways we could represent environments, things like sets. Or you can split the environment into two lists, two flat lists, instead of an association list. One is a list of variables, one is a list of values, and you walk down both lists together. Whole bunch of different ways you can represent environments. They have different trade-offs, especially when you get into miniKanren land and trying to prevent divergence or infinite loops when there is no answer. It all comes down to, when there is no answer, how do you cut that off? How do you cut off the search and make sure that miniKanren stops looking when instead of going on forever? And I've got the beginnings of a gigantic blog post that goes into fantastic detail about how to represent environments, and I need to clean that up and put that online. But it's subtle. Let's just put it that way. Very subtle. Let me go ahead and check this in, by the way. All right. So I've posted. So now, if you're following along online, I've got. I posted in the lookup O. All right, and you can play around with that if you want. And now we're ready to go on to the valexp. Let's see. I think we got some questions in chat first. Let's see if there's anything in this. Are there rules to translate scheme to miniKanren which tells you when you need to add this quality constraint? Asks Orchid, Orchidacea, something. Good question. So when do you need the disequality constraints? When do you need this equal thing when translating from scheme to miniKanren? One way you can look at it is if we go back to the original lookup, the original lookup. Okay, if we look at the original lookup code, there is an implicit notion of ordering with the p-match, right? So we could swap in lookup. We could swap the lines like this, the clauses like this, because if the environment is empty, the first two clauses just won't match, because the empty list or the empty environment is just represented as an empty list. Empty list won't match these since they're pairs. However, if we were to swap these two clauses, then the program wouldn't work. It wouldn't work because these two patterns overlap. This pattern and this pattern, they actually overlap. I could make this the same exact pattern if I want. Instead of an underscore, I could make it a V, and then you can see that they really are exactly the same pattern. The only way in which those two differ is in the guard. So if I really wanted to be careful, what I would write is a guard saying that X and Y are not equal in this case. Okay? And as long as I'm careful and write that guard explicitly, then I could reorder these clauses with abandon, and they would always have the same exact behavior. Okay? And Edgar Dijkstra talked about this idea to some extent. Guarded, Dijkstra guards was the idea. So there's an implicit notion of negation that we can make explicit as long as we're very careful with all of our tests. And you could do this in a cond also instead of a p-match, right? You could add an and have additional side conditions that encode all of the rules necessary to match things. You think about it this way. If someone could come in and reorder your clauses any way they pleased, would your program always have the same behavior? If not, you should be a little more explicit about any side conditions, things like that. And as soon as you add this explicit guard, then you see the negation. There is a not EQ there. Okay? So that is really metaphorically what lookup is defined as. In fact, I'll add this as a comment. This is the metaphorical definition of lookup. That's the Dijkstra style guard. Okay. So if you write your programs this way, then you will make the side conditions explicit, and that not EQ. Okay, so this is sort of like a unique or something if Scheme had that. So in Scheme we write that as not EQ, but that not EQ is the same as this disequality constraint. Okay, so that's where the disequality constraint came from, right? Yeah, guarded command language, David Kahn points out. So yeah, you can look up guarded command languages and things like that. Okay. All right. So miniKanren makes us be more careful about expressing things like those hidden clauses, or sorry, the hidden guards, because every conD clause gets tried, right? So we can't rely on ordering of the conD clauses to prevent us from getting into trouble with the guards. We have to be explicit about it. Okay, good question. Okay, so that's lookup-o. Let me go ahead and check this in, make sure it loads again. A little paranoid about it, good. Okay, so I'll go ahead and check that in. Okay, so that's lookup-o. Now, and of course, lookup-o, assuming we did it right, lookup-o should be able to play all the games we know and love, right? So if the answer, should be 5, if the answer should be 5, then we should be able to say what variable gives us 5 in this environment, and sure enough, it's X. And if we ask for another answer, there is no other answer. Okay, run start gives us back just X. Okay, so we can do all those sorts of things, put variables anywhere we please, and just works the way it does with any other miniKanren program. Okay, so we have a lot of flexibility. I guess I may as well include that query as well. Okay. All right. So we have a more flexible version of lookup that's actually quite short. And if you rewrote this with matchy instead of fresh and conD, you would see that the lookup-o definition is actually shorter than lookup because we don't need to handle the error case. So that's interesting. Like, we're being more declarative in a sense. Like, we don't need to handle those little details. We just fail. So we have a very high-level description if we go to the pattern matching version. It's already pretty high level, and we're treating it as a relation. Okay, nothing impure there. All right. So now the next thing we have is our friend eval_exp. Okay, and just to make it a little easier to read, I'll get rid of some of these comments. Okay. So this is what we're trying to get working. Okay, and I've got. I'll keep it commented out here so we can look at it as we write our eval_expo. So we're going to define an eval_expo. And what are our arguments going to be? So before we took expr and in, we're going to still take those. Now we're going to have an out. Represents the value of the call to eval_exp. Okay. Instead of pmatch, we're going to explicitly use conD. Once again, we could use matchy if we wanted to. It's up to us. And we have 3 clauses, right? One for variable, one for abstraction, one for application. So we can try writing this like a step at a time, just like we did before. So I'm going to go ahead and grab our comments for the 3 clauses. And we have an application. Okay, cool. And we could do the similar technique of trying to test things a little bit at a time. Now, one thing we want to do is make sure we have the right patterns, right? So metaphorically, we're matching against the expression. So for example, with an application, with an abstraction, with a lambda, we want our expression to look like this. Okay? So we have to be explicit about backquoting our expression. And the other thing is we need to introduce some fresh variables that are used in the expression. But otherwise, the pattern looks actually very similar. It's exactly the pattern. I mean, I just copied it literally. It's the same pattern as for the abstraction down here. So that's nice. Okay. So that's our pattern. And if that works, then we do something. Eventually, we're going to try to unify out with something. Okay, what about our application pattern? Our application pattern looks like E1 applied to E2. So we're going to do a similar thing. We're going to say that the expression, just add our back quote, is E1, E2. Once again, we need to add some fresh variables for E1 and E2. Okay, so that's our application clause. Should match that. And now,
can I get some fries with that, Jake?
Oh, wow. Is our troll friend back? Hold on.
Have fun, mate. What's going on? What's
Hey!
that?
How's it going?
I'm so fucking high.
All right. We used to have a troll that would come and hang all the time, but anyway, that guy is not our traditional troll. That's too bad. I hope he's doing okay. Anyway, so let's do the variable case. So we need okay. So once again, we have like the do something, right? So so we're going to do something in the application case, do something in the abstraction case, and then we have the variable case, and we're going to do something. The variable case. The question is, what pattern do we have for the variable case? Well, if we look down here, we're matching against anything, any pattern, and our guard is that thing has to be a symbol. Okay. Well, how do we express that? Ew, that sounds tricky. We could do it a couple ways. One is we could explicitly tag all of our variables, right? So we could do something like, say, if we have an expression and the expression happens to be something like var tag, comma x, right? Then we say, hey, that's a variable. All right? We could definitely do that. Don't look like write a program that does tagging and untagging of programs, but that gets tricky once you have logic variables inside your program. How do you tag a logic program, or a partially instantiated program that has logic variables in it? That's not so easy. So there are a bunch of reasons that, from readability to other reasons, to try to avoid the tagging, and it's a trade-off. Tagging makes things simple, it's very general, and so forth. And Lambda is really a tag. So, this Lambda thing really is a tag for the Lambda expressions. Not having tags, not having application being tagged in a scheme means that, sometimes the application clause is going to overlap with the Lambda clause, for example, once we have multiple expressions. Once we have like E3, if we could have an E3 there, now those lists are the same length. And now we have to explicitly say that E1 isn't a Lambda, but then we have to make sure it might be, where maybe it's shadowing. I mean, it gets tricky. So tagging has its advantages, but we're going to avoid tagging in our case. And instead, we're going to say, hey, look, we've got the symbol guard, right? Well, let's do something similar. So we've constructed a new, miniKanren, or at least most new versions of miniKanren support a constraint called symbolo. So we can say expert is a symbolo. What is a symbolo? Okay, well, let's see how that works. If I do run one q, symbolo q, what I'm asserting is that q represents a symbol. And we can see in the output, even though there's only one answer is wrapped in this extra list, the reason there's an extra list is that we have the side condition saying that _0, which represents q, is a symbol. Okay, this is a symbol constraint. So if we try unifying q with a symbol like quote foo, well, that succeeds. And now we don't need to see the symbol side constraint, or constraint, because we already have a symbol. If, on the other hand, we try unifying q with 5, which is not a symbol, it's a number, then we get back the empty list. It failed. Okay. So symbolo is a type of very simple, it's a type constraint. It's a runtime type constraint. It's very simple. It only works on these atomic values. They're symbols, but it gives us some expressive power. The other thing we have that's similar is numbero, or numbero. however you want to pronounce it. And here we have a psi condition saying that the thing is a number. So in this case, if I unify q with 5, that succeeds, and we throw away the constraint because it can't be violated anymore. If I say q is a symbol, then it fails. Or I could say q is a list 5, and that's going to fail because a list 5 isn't 5, it's a list. So symbolo and numbero allow us to specify basically psi conditions as something has a certain type, or if it becomes ground, it has a certain type. Okay? And that's what we need for variables. The other thing to note for things like symbolo and numbero is that if we reorder the unifications, symbolo works just like equal, disqualify, constraints, whatever. The ordering doesn't change the semantics. So having modulo divergence, of course. But having the unification of q come before the symbolo constraint, that doesn't matter. It can come before or after, has the same meaning. Okay. All right. Dimitri asks, can we avoid using symbolo by putting variable checking case last? Last, we cannot, because unfortunately with, not unfortunately, it's sort of inherent to how it works. Cond can try any of the clauses it pleases. And in fact, if you do a run star for your query, cond will try every single clause. So unlike cond, unlike if, unlike pmatch, we can't assume that just because we have a clause that comes last, that the other clauses above it have failed to produce answers. They may have succeeded. Now, one caveat to that is we could do something called committed choice, which there's a committed choice operator in Prolog, for example, or Mercury, things like that. And miniKanren supports 2 of them. One's called conde, one is called condu. And I talk about them in my dissertation. There's a chapter about them called On Thin Ice and a Reason Schemer. They allow you to write something that's much simpler to, or so much similar to the traditional scheme cond, where if and there is a distinction between how conde and condu works, but anyway, for conde and condu, it's much more like cond, where you have an expression in test position. And if that test succeeds, then you commit to the particular clause you're on, and you guarantee you'll never try any of the later clauses. Okay, and that is a way to do things like negation as failure, which is used a lot in Prolog and so forth. It gives you a lot of power, especially for expressing negation, for pruning the search tree, making it more efficient. I think a lot of people using core logic use conde and condu. Okay. One problem with conde and condu is that they're not pure declarative operators. They actually are sort of side-effecting operators from a logic standpoint. You have to use them extremely carefully, or your programs become unsound. You can start proving things which aren't true. The other thing, and the reason I'm avoiding them here, is that conde and condu, or committed choice operators, they inhibit your ability to run backwards in cases. So here I'm interested in trying to write an interpreter that could generate answers wherever you put logic variables. It'll try to fill in the logic variables. I don't know how to do that in a pure way with the committed choice operators. So I'm gonna be extra pure here, try to stay as declarative as possible, and avoid that. But you're absolutely right. We could do something that would more mirror the regular semantics of something like cond in the Lisp, and then just put the variable case last, and then we wouldn't need symbolo. Okay, so that's absolutely correct. That's a good question. We're going to try doing it sort of the higher level, more declarative, more pure way. But of course, all of these approaches have trade-offs, right? If you're doing this in Prolog or Mercury, you might want to use the committed choice operator and then just put the symbol case last, and then you wouldn't need something like a symbolic constraint. Okay. Good question. All right. So let's. Okay. So now we have the symbolo case. If the expression is a symbol, that means it represents a variable. And that's exactly the same as with our eval x before, the scheme version. Okay. And in that case, we just called lookup, right? When we have a symbol, we just look up the symbol. And the only difference here is that instead of being called x, it's still called expr. And of course, instead of lookup, we have lookup-o. And lookup-o will return some value if it succeeds. And the value it returns, or the value it associates with the third argument, that's what we want to return, put in the output position from eval expo. Okay, so the symbolo case, just doing a lookup using our lookup-o that we already defined. Okay, and in theory, at least, we should be able to run it. No? Sure, it runs. Okay, so we should be able to do eval expo. Whoops. So eval expo of some symbol x in, let's say, in some environment where x is bound to 5, and then that we want to associate that with q. Sure enough, that worked. If we do a run 2, it blew up because this lambda clause, we forgot to put our x and body in as fresh variables. Okay. Okay, good. Let's try it again. This slightly updated definition. Okay, so if we do a run star at this point, none of the other clauses hold, so we're only getting 5 back. Okay, so we already have a running, very simple interpreter that can only look up variables, but it works. Good. And should be able to run it backwards to some extent and all that, as long as we're not overlapping with these other clauses. Okay, so we handled the variable case. That was easy once we had lookup-o. That's done. The abstraction case. The abstraction case is also going to be really simple because all we did before was return a data structure, return something representing a closure, a tagged list, a closure list. Okay, in that case, we're just going to return exactly the same information. But of course, we don't return values. We associate values with output. Like that. All right. Ooh, oops. I think there's like some new Unicode support in Emacs that's driving me a little bonkers. Okay. Anyway. So we're going to just return the closure, some representation of the closure in the Lambda case. So let's test that out. So I think one of the meta lessons here is that even though I've written probably thousands of interpreters at this point, I'm very, very humble when it comes to testing the behavior because I know how easy it is to mess it up. So I always want to test every single clause I'm adding whenever possible. Okay, sure enough, get back a closure. Great. And I used a run star. That means there is only one answer. Perfect. I could do more testing here, obviously. But because this clause is so simple, I think we're probably okay. All right. So now the application case is the only case we have left, and that was the more complicated one, right? So we had to evaluate E1 and E2. E1 had better be a procedure, which was represented as a closure. We pattern match on the closure, and then we make a recursive call and evaluate the body in an extended environment. So we're just going to do exactly the same thing. Exactly the same thing. Let me split the screen so we can see this code. All right. So what are we going to do? Well, we have to make a recursive call to eval expo and evaluate E1 and E2. So we're going to evaluate E1 in the current environment. So in fact, the arguments are going to be the same in this case, first two. So we're going to evaluate E1 in environment, and that's going to give us back proc. So I can just say proc is the name of the output and add that as a fresh variable. So, if we look at the temporary names we're assigning these values using the let, we can use those names as the output, name of the output arguments. Okay, so it just makes it a little simpler when translating. So I can actually grab the call. Now this is eval expo. Okay, the first two arguments are the same. That's returning something called val. Well, we'll just make the output argument called val and make sure to add that to our fresh argument list. Okay. So those two are the same. Now it gets a little more interesting. Proc had better be a closure. So let's go ahead and unify proc with this closure. And make sure I've got my back quote. Once again, I need to make sure that I have my variable names that are being added. Okay, x, by, and inf need to be added to the list of fresh variables. Okay, great. So if I have a procedure, and in this case, I want to make a recursive call. So that's about expo. First two arguments don't change any. And then, well, what's the output? What's the value? Well, it turns out that the value of this call to val_exp is the value of this recursive call. This is in tail position, we'd say. So there's nothing else that has to happen. Once we know the value of this call to val_exp, we have the final answer. So the third argument, the so-called output argument of this val_expo, is just going to be your out, our third argument to val_expo up top. So that's it. You know, that was a fairly straightforward translation of this code. If I want to, I can simplify things at least a little bit. I can notice that I've got a temporary here, a variable I'm reusing in a couple places. So this proc, which I'm matching against to be a closure, okay, that's the third argument to this evaluating E1. If I wanted to, I could actually inline this and just say that the value of the when you evaluate E1 and env, that had better give you back this closure. And I'm going to write it this way. It lets me get rid of this variable proc. But most importantly, when I'm running backwards, I can't assume I actually know what E1 is or what env is. I might have to, you know, this is very tricky. I might actually have E1 might be a fresh variable, right? So I might know the output completely. I might know what the closure is, but I might not know what E1 is. I might be actually trying to figure out E1, not the result of E1. So I want as much information as I can as early as possible. If I want to know that if E1 isn't a closure, that I'm going to fail immediately. That's sort of. The other thing that I have to be really careful of is these names. If you notice, I have env here and env here, and then I have some other ones, env here and env here, because I just pulled names out of this code. However, I actually made a mistake. And if you're paying careful attention at home, maybe you saw the mistake. Remember that I've got an environment coming in to val_exp, and then I'm using that environment twice. So these two envs are the environment coming in up top. But when I p-match against proc, I'm matching against a closure. I'm matching, you know, proc against this closure list, and that env is really a different env than these two. Metaphorically, that env is an env hat, and when I extend the environment, that's an env hat. Okay, so this env is completely different from these two envs and that env. So if I'm not careful when I'm doing my kind of copying, paste, moving things around, I'll end up with the wrong environment, and I'll end up with dynamic scope instead of lexical scope, which is not what we want. So when I come back up here, I need to recognize that these two envs really are the env I had coming in, but the environment stored in the closure, that is a different env. The other thing is when I just move the env here, actually let me take a step back. It's actually worse than that, because when I introduce env as a variable, because I say, hey, I need to have this closure and I've got an env, I need to go ahead and add env, what I ended up doing was shadowing all the envs. So this env is a new fresh variable. Every use of env, all four uses of env in this code, is going to refer to the new logic variable down here. None of them will refer to the environment that was passed in. Okay, so I really have done bad things with my lexical scoping and environments and all that. So I need to be very careful and make sure that I'm using the right the correct environment in each place. Okay. So one way to do that would be just to recognize that in my original code I was shadowing the environment with this env_hat, and therefore I really should go ahead and rename things in my eval_x code before I write the miniKanren code. Okay. All right. At this point, I believe we should have a running version of the interpreter. And yeah, okay, so I'll just have to make up some tests, I guess, for it. Let's see if I can. So I can load it. All right. Okay, so we got a couple tests. Go ahead and start adding some of these tests. So we have a simple lambda. It's going to give us a closure. We can have more interesting tests, like an application or variable. Well, I don't know if the variable is more interesting, but we can look up x in an environment where x is bound to 5. That should give us 5 back, and it does. Okay. Now let's try the hard one, which is application. So let's try applying lambda xx to lambda yy, let's say. In the empty environment, let's see what that gives us. It gives us a closure, which it should. Okay, gives us lambda yy. Okay, so far, to the extent I've tested it, looks like it behaves the same. If I really want to be careful about these things, I should start doing things like testing the lexical scoping and the shadowing. So we might have lambda xx, lambda xx, and now I want to do an extra application and look up the values and things like that. Make sure I'm getting the right closure. The easiest way to test this is actually to extend the interpreter to handle more forms. And then we can write programs like factorial 5, make sure they work, and then we can comment those out if we don't want them. But anyway, I'm going to declare come on, Emacs, don't freeze up on me. Okay, Emacs managed to quit on me. Okay, so that's, let me bring Emacs up again, but otherwise it seems to be working. Okay. So I think, since we've gone over 2 hours already, I think the thing to do is to add the other features that we might want. Add things like quote and list, and maybe numbers and conditionals and all those sorts of things. I think we should probably add that in the next Hangout, just because that'll take a little while. And I wanted to go slow. I mean, I think there's enough complexity here. There's a lot going on. If these interpreters look simple, it's because you haven't played around with them enough, because they really are very subtle. So I want to, instead of trying to rush through the rest of it, I would rather take some time and for the next Hangout actually go through extending these interpreters in some depth. But you already have enough interpreter to play around with for both of these, in both the Scheme version and the miniKanren version. If you want to try some things on your own, some homework if you want to think of it that way, some things you can try. You could try doing things like adding numeric constants. Remember, you have numero. I'm not talking about addition. I'm just talking numeric constants like 5. You could try adding booleans. You could try adding conditionals like if. Okay, try adding these both to the Scheme interpreter, get that working, and then try adding it to the miniKanren one, running it backwards. You can also try adding things like 0 question mark, or add booleans, add boolean question mark, add some type predicates, for these atomic values. If you really want to be ambitious, add cons and car and cdr. You can also try adding things like quote and list, which are what we're the things I want to show next time. If you really want to be ambitious, try adding real numbers, tag numbers, using the Olig number system that's in my dissertation and in the recent schemer, using these lists of binary integers and doing arithmetic over those. That turns out to be really interesting, and it's also quite tricky to do. The other thing is, if you want to look ahead, I can and will post a list to a paper we have on writing these relational interpreters, where we extend it with lots of things. If you really want to go overboard, try adding things like call CC and continuations and stores, and you can go to town for this, right? Implementing small step CESK machines, and now you're already kind of in the research, not kind of, you're definitely in the research territory that we're trying to do, because we don't know how to do some of those things very well. We don't know how to do a lot of those things very well. Some of the things work really well, remarkably well, and some of the things that look like they should be about the same level of difficulty turn out to be much harder, it seems. Or we just don't have the right set of constraints, things like that. Okay, so anyway, you already have enough to start playing around with these relational interpreters. Next time we'll add other features to the language, and things will get a lot more interesting, and we'll start running things backwards for real. You already can try to run them backwards. So let me go ahead and check in everything, and okay, that's all pushed. You can knock yourself out. Yeah, I'm glad you found that interesting. Thank you. And thank you for your question. Yeah, so that's it. If anyone has questions, I'm happy to try to answer them to the best I can. I'll also try to answer. There are a couple of questions in chat. One question from Vanilla is, how do we know that symbolo and disequality constraints, the equal/equal, are pure, even though negation and committed choice aren't? Well, that's a good question, and part of the problem is, of course, what it means to be pure. Pure with respect to what is sort of the real answer, right? Like, what do you mean by purity? To me, in a logic program, it's very important that you be able to reorder your goals any way you want and not change the behavior, other than maybe the infinite loop versus failure when there is no answer. And the committed choice, the Condé and the Condu, they completely violate that. They also seem to inhibit your ability to generate answers when you put logic variables in your program. And there's just kind of a whole set of issues that come up when you're dealing with negation in this approach. So Condé and Condu, once you have those operators, I'll put it another way. Once you have Condé and Condu, you can do pretty much any dirty thing you could possibly imagine in the language. You can implement pretty much anything. You can start telling if a variable is bound or not. You can tell if a variable is fresh. You can use it to implement every dirty operator you can imagine, basically, or probably close to it. So they give you the power to sort of peek under the hood and tell whether or not a variable is bound, for example. You're not ever supposed to know that in the pure model. If I give you an x, you don't know. If I give you an x and you unify x with 5, you don't know if x was bound before. X could have already been 5, or x could have been fresh. There's no way to tell. So as soon as you have the ability to start telling, you can start doing all sorts of hacks that break all the semantics of miniKanren, the pure semantics. So with disequality constraints, disequality constraint is an extremely weak form of negation. All it says is these two terms aren't the same. But there are infinitely many terms in miniKanren. So if I say x is not equal to 5 with a disequality constraint, because there are infinitely many other values, even infinitely many other integers, that's a very weak form of negation. So for example, you can't say that x isn't a pair using disequality constraints. You might think you could say disequality x to the pair y.z. All that means is that x isn't the single pair x y.z, because metaphorically the pair y.z represents a single pair, maybe the pair 5.6. So whenever you know more about y, you know more about z, maybe they even become ground, x can't be that particular pair. But you can't express with disequality constraints that x isn't any pair, at least not just with disequality constraints. You might be able to do it with some other mechanisms that we don't support right now. But So disk-quality constraints are extremely weak. With conde and condu, you could express, that x is in the pair. You could express all sorts of other stuff very easily. So with great power comes great danger, I guess, in the logic programming sense. And you can easily kind of lose all of the niceties of being high-level and declarative by using operators that are too powerful and let you kind of peek under the hood. And at that point, you're kind of not that far from programming in C in a way. You've kind of lost all of the logical niceties and all of the high-level declarative aspects. So you have to, there's a trade-off. Sometimes, it may be very convenient, or for the problem you're trying to solve, you don't care about running backwards, you don't care about putting variables anywhere. There's a particular problem you're trying to solve, and the logic programming paradigm, or the backtracking search, or unification is useful for you. And in that case, if you know what you're doing and you need conde or condu, or whatever, you want to use some impure operator, just go ahead. That's fine. A lot of people do use that, especially in core logic. If it solves your problem, that's great. If you're trying to stay close to the semantics, close to the logic, close to the math, whenever you start using something like conde or condu, you should ask yourself, well, is there another way to do this, right? Because when you look at the mathematical rules, the logical rules written down for a formal system, usually there isn't a notion of ordering. Or if the notion, the notion of ordering, a lot of things happen in parallel or metaphorically or independently, or the ordering doesn't matter. You have to be very careful once you start using conde and condu, because the ordering does matter then. Okay. That's a good question. Daniel asks, I was thinking about this question when I asked the variant of it last time. Since you can do relational untyped lambda calculus with unification, my interpretation is that disk quality allows you to express non-overlapping clauses and get interesting answers without exponential explosion around each condition. Okay, well, the question of interesting answers is a very interesting question. I would say that you need if you use tagging, then you could just use conde and different tags. You tag your variables, tag your application, tag lambda. Then you don't need the disk quality constraint, or you don't need symbolo. Okay, you don't need symbolo to tell variables from other types of expressions. First of all, so you don't need symbolo then. Another thing that you don't need is in lookup. That gets tricky. Okay, so in lookup, what you could do is assign a unique identifier to each variable, or not allow shadowing of variables, or you could do like nominal logic, which is nominal logic programming, which is a cool thing, which I should talk about at some point. There are other ways to try to get around it. You could use a substitution-based approach. There are lots of ways you can kind of get around this problem of shadowing. If you don't have disk quality constraints, then then the standard version of lookup-o that we wrote, that's not going to work correctly if you allow shadowing. And furthermore, sometimes you'll have infinite loops that you could cut off. So as long as you don't have any shadowing in your program, you don't have variables shadowing each other, then it works just fine. You might have some infinite loops when there are no answers, that sort of thing. As far as the combinatorial explosion around each condition, yes. So once again, well, even that with the conditions, if you depends how you treat conditionals, like if. If you treat it as in scheme, where hash f is the only false value and any other value is true, then it's very handy to have disk quality constraints. I should talk about that next time. Because then you can say in one conde clause, if the test evaluate is equal to hash f, then do the false branch. If the test expression evaluates to some value which is not equal, disequal from hash f, do something else. And that's a really handy thing to do instead of trying to enumerate all the infinitely many possibilities that aren't hash f. So that allows you to avoid an explosion when you have conditionals. So that part's absolutely right. You could however, change the semantics and say we're not trying to do scheme exactly. We're trying to do something more like ML, where you have a true value and a false value, like you actually have real booleans required. And in that case, you could just unify directly against hash f or hash t. And in that case, you wouldn't need the disk quality constraint to avoid the explosion. So part of this is we're dealing with schemisms, right? So scheme Scheme's kind of a loosey-goosey language when it comes to things like Boolean values and truthness, I should say, right? So it's kind of like Perl in that. Perl's even worse, I guess, because Perl has multiple false values, I guess. Anyway, yeah. So these are all trade-offs. This depends on how you want to model the language and so forth. But yeah, avoiding exponential explosions when you don't have to is really important. And also avoiding infinite loops when there is no answer when you can do it is really important. So disk quality constraints are really handy. Symbolo is handy. These are handy things. You don't need them. You know, it's already a Turing-complete language without them. But they are very handy in modeling things. In fact, that's one area of research we have going on right now is to try to add more type constraints like Symbolo and Numbero, but to make them a lot more sophisticated and let you express arbitrary data types. Some work I'm doing with Michael Adams at the University of Utah right now. So anyway, yeah, that'd be fun to talk about also. So that's it for today. Went a bit over, but you know these interpreters are really complicated. So we're just seeing the kind of the very beginning of the interpreter stuff, but they're really fun. I mean, once you know how to write interpreters, then you can implement your own languages and change the semantics very easily, and it's really fun to run the programs backwards and all that. So we'll play around with that next time. Next time we'll generate quines and so forth. That's it for now. Thanks everyone for joining me, and the code's on the website. And I'll post some links to things, and I will see you all next Sunday. And I'll stop the broadcast. If anyone has other questions or they just want to chat, let me know. I can hang out for a couple minutes. But otherwise, I'll see you next time.